Swayam Prabha. Digital India. Educated India.
I want to be able to approximate the matrix vector multiplication by using an importance sampling. I have shown using a simple example how importance sampling helps you to reduce the variance. Once I understand an aha of the possibility, now I am going to extend that idea to sampling columns. So the whole thing reduces to defining the probability of selections of the columns of A. So what is a good sampling distribution for selecting from the columns of A? So earlier x was a scalar variable. Here x is going to be columns. So I am now going to be talking about a random vector. Matrix vector product consists of sums of weighted columns of A. So this is the jth column weighted by Vj. I am now transforming that, scale it by the probability Pj, and we say the random vector x takes this value with the probability Pj, where j is equal to 1 to n and summation Pj must be equal to 1. I hope you got the idea now. In the previous example, x took the value a1, a2, I scaled it by p1, p2 by dividing a1 by p1, a2 by p2. Here x takes the value aj, pj, I am going to select the columns randomly with the probability pj. So if I picked a particular column times a scalar vj, I am going to choose that with the probability pj. I do not know what pj is, but pj is the number I am going to compute. I am going to divide that column by pj, dividing a column by pj, multiplying a column by pj, pj is a scalar, is equal to dividing or multiplying every element of that. Therefore, in my sampling procedure, I am going to pick the scaled version of the jth component of the matrix vector product as a random variable with a value like this with the probability pj. So if I did that, what is the effects? This is the jth value of the random vector value, pj is the probability, pj gets cancelled, that is equal to summation, that is equal to av. Wow! Now you see the same idea that is in scalar comes in here. So in 1998, FKV, 1998, you remember FKV, Fries, Kannan and Vempala, 1998. This is the idea that was first expressed in their 1998 paper. So FKV is an important paper in the analysis of randomized algorithm. And you may know Kannan is a well established applied mathematician, computer scientist. He works for Google in Bangalore. He is a very senior researcher in Google research in Bangalore. He was trained in the USA. He worked in the USA for a long time. He was in academic departments. Now he works for Google research in Bangalore. So this essentially tells you x is an unbiased random vector. What is variance of x? I have already told you how to compute the variance of x, which is given by this formula from page 2a in page from expression 2a in page 1 of this module, which when you substitute the individual value, this is one term, this is another term, The second term is a constant term which is independent of Pj. The first term depends on Pj. So, this is the variance. Now, please understand the same pathway that we used in scalar estimation also comes in vector estimation. So, I need to be able to choose Pj that depends only on the first term, because this is the only thing I can control by controlling Pj. Therefore, I am going to talk about the column selection, the distribution that depends on the square length of the column of A. So, this is the length squared column of A is the distribution that is going to decide Pj. So, the choice of Pj depends on the first term on the right hand side of phi. Now, I am going to show the distribution Pj is the distribution that is going to be dependent on squared length of the columns of A. So, this means I am going to pick the column J with the probability Pj, and the Pj is going to be the ratio of the square of the norm of the jth column to sum of all the square of the columns. Please understand, the sum of the squares of all the columns is simply the Frobenius norm. Just to be able to recall, what is Frobenius norm of A? The Frobenius norm of A is square is defined by sum of Aij square. So, the Ai, the summation with respect to I tells you the sum of the square of the elements of the given column is over all columns. So, this is equal to summation over j of the 2 norm of the column j, and that is equal to, so the sum of the 2 norms is simply the Frobenius norm of A is essentially the sum of the squares of the 2 norms of the columns of j. Therefore, this quantity is Pj, and you can readily verify sum of Pj is equal to 1. This is very similar to P1 star was A1 by A1 plus A2, P2 star is A2 by A1 plus A2. What is A1, A2? A1, A2 are the 2 values of x. That means the probability is data dependent. Here the probability depends on the properties of the columns of A. Properties Pj proportional to the length of the square of the columns. You substitute 6 in phi. Let us go back. What is phi? Phi is the expression for the variance. In analogy with the scalar example, I am now going to make a leap forward. I am going to pick Pj proportional to the square of the length of the columns, and this ability to leap forward is based on our experience with the scalar variable. So, I have expression for variance of x. In here I am going to substitute 6 the expression for the variance of x. So, this quantity now cancels each other, that is equal to 1. So, this is the constant that comes out of the summation. So, that is equal to the Frobenius norm times the summation of Vj square minus Av, the norm of the Av square. So, this is the product of the Frobenius norm times the square of the 2 norm of V minus Av square. Now, if x is, if we say A is less than B minus C, then you can definitely say A is less than B, where C is when C is positive, B is positive. So, if A is less than B minus C, we can essentially say I can drop C. If I drop C, I am increasing the right hand side, so it is called inflation. So, by inflating the inequality, I simply say the variance of x is less than or equal to the product of the Frobenius norm times the 2 norm of V. Therefore, what is the selection probability? The selection probability is the LS column A. What is that? This is the best estimate of the distribution for picking the columns of that. So, this is the distribution that depends on the squared length of the column. Squared length is called length LS. So, LS column refers to the important sampling probability, important sampling IS probability, which is given by P1, P2, Pn. Pj is 1 and Pj's are given by 6. Let us go back and what 6 is. 6 is essentially Pj is equal to square of the energy in the jth column divided by the sum of the total energy in all columns, which is measured by the Frobenius norm, So, now I want to be able to come back to the problem I stated. I want to solve that. So, to approximate AV, now I want to get a good approximation. For example, I want to give an sample idea and then come from there. Suppose I have a coin that falls head with a probability p and the fall tails with a probability 1 minus p, and I simply say x is 1 with a probability p, x is 0 with a probability 1 minus p. The expected value of x is p, the variance of x is pq. So, I can use the result of one toss to predict or to estimate the probability. But if I took k tosses, I can represent y is equal to sum of xi, the expected value of y is equal to kp, and the variance of y is equal to kpq. So, that is the idea. So, if I am interested in estimating the probability of a coin falling head, y is equal to 1 over k times summation xi, E of y is equal to 1 over k times summation expected value of xi. Each of the expected value is p. I am adding p k times, kp times kp is equal to p. So, expected value is equal to the unknown, but the variance of y is equal to 1 over k square times the variance of sum of the variances of xi. The sum of the variances of xi, each of them is equal to pq. So, this is k times pq divided by k square, which is equal to pq divided by k. Why is this important? If k is 1, the variance is pq. If k is 2, pq by 2. When k is larger than 2, the variance reduced by pq by k. That means by taking the average of the results of k consecutive samples, I am going to get an estimate which is the average of the results of the k experiments. The estimate is unbiased, but the efficiency is 1 over k times, the variance is 1 over k times the variance of single toss. So, by conducting the experiment several times, I can reduce the variance by the number of times I am repeating the sample. So, this is an idea which is an age old idea in statistics. I am going to borrow from that idea. So, what is that we need to do? I need to be able to pick one of the columns of A. If I picked one column by one sample, I get an estimate. We already showed the estimate has certain variance, certain mean and variance, but I can reduce the variance, and that variance itself is the best variance you can get because of choice of pi. But we are greedy, we would like to be able to reduce the variance even further. The further reduction of the variance can be obtained by performing S trials with replacement. This is equivalent to doing multiple tosses of a coin. So, you take the average. So, what is the average? The average is a vector y. And what is this average of? Average of the jth column scaled by Vjt. What is that? It is the scalar multiple of the jth column with the jth element of the vector v scaled by Pjt. This is the value of the random variable in one selection. I am going to have S selections. So, this matrix is going to be the sum of these, the average of these, 1 over S of this. So, the best estimate of the matrix vector product y is given by the average of the S selections made according to the sampling distribution, and that is an approximation to AV. Please understand, this is the random variable xt at the tth trial. So, this is 1 over S summation t is equal to 1 to S x of t, and this is the summation over t of x of t by A. So, the variance the expected value of E of y is 1 over S times this. The variance of each of this is constant. So, S times AV divided by S AV, that means y, which is considered the average, is an unbiased estimate of the matrix vector product. The variance of y is going to be 1 over S square times the variance of x of t, and using 7, the variance of x of t is less than the product of the Frobenius norm of f times the 2 norm of v. That is for 1 x of t. The variance of all the x of t's are bounded by the same quantity. So, I am going to add this quantity S times. So, the numerator is S times this, the denominator has got S square. So, S square gets cancelled, leaving behind 1 over S times this. That means, by repeating the experiment S times using the sampling probabilities, the sampling probabilities minimize the variance in single pick. By repeating that S times, I am going to further reduce the variance by a factor S. So, we could essentially understand how the repeated sampling is going to help the variance further. This completes our exercise on the forced randomized algorithm to solve a very simple problem of computing a large vector by a large matrix. How do I approximate the matrix vector product using a clever importance based sampling approach, where I control that the estimate of the unknown, which is the matrix vector product, is unbiased, is minimum variance. The probabilities are decided by minimum variance condition. I bring about further reduction by repeating the experiment S times. Please understand, the whole thing rests on the distribution LS column of A. If I can have column based sampling, I can also have a row based sampling of A. So, the row selection of A, the column selection of A, everything based on squared length distribution. So, we could have done a row sampling as well using a similar argument to get RSA distribution. So, I have a distribution to pick columns, I have the distribution to pick rows. Instead of doing both at the same time, I did for the columns and then said I could have repeated the same show by replacing column length, square of the column length by the square of the row length. Now, I am going to talk about the second application, second problem. The first problem is computing matrix vector. The second problem is computing matrix product. So, I am trying to introduce the randomization algorithm using simple problems. I always say you have to learn to walk before you run. So, this is the exercise by which we learn to walk along the paths that is already established in the literature for randomized approach to a linear algebraic problem. The second problem is matrix product problem. We have already seen computing a million by million matrix problem on even the teraflop machine will take over 11 days. So, I would like to be able to approximate the matrix product. I am going to talk about sampling based ideas. So, I am going to carry the sampling based ideas a little further to solve few other problems in linear algebra. You please understand there are three ways of multiplying matrices. One is the inner product, another is using columns. So, how do I compute the matrix product? One is the classical solution Cij is equal to summation Aik Bkj. You pick the ith row and the jth column, you run k is equal to 1 to n, you compute the inner product of the ith row and the jth column. This is the inner product based definition of a matrix product. A matrix product can also be thought of, this is C, this is A, this is the B. So, the first column of the product is essentially take the first column of B, you multiply the first column of A with the first element of the first column of B, second column of A with the second element of the column of B. So, A times B star 1, what is that? The whole matrix A multiplied by the first column of B gives rise to the first column of C. A multiplied by the second column of B gives rise to the second column of C. So, I can recover C either element by element using the inner product or by column using matrix vector product. We already know how to compute matrix vector product a minute ago. So, this is the product of the matrix A with the column, first column, product of the column matrix A with the second column, kth column. So, apply the matrix vector product routine k times and collate the results. You get the matrix C. If n is the number of columns of A and the rows of B, because the number of columns of A and the rows of B must be the same for compatible for multiplication. So, if I picked a particular column, I should be able to pick the corresponding rows. So, here I am trying to express I am going to recover C not as the elements, but as columns. So, if I can pick k columns of B with the important sampling, I can multiply each of the k columns of B by the matrix A, then I would get k columns of the product C. The probability of selection is Pi, summation Pi is 1. So, now I am going to define a random matrix. So, look at that now, how I am going to define a random matrix. So, in the case of in this case I am interested in discovering the product matrix C itself. There is another way of recovering the matrix product is like this. This is the matrix C, this is the matrix A, this is the matrix B, A and B. So, what is one way to put it? I take the first column and the first row, get an outer product. I get the second column and second row, get an outer product. I get the nth column and nth row, get an outer product. So, the product matrix C can be recognized, can be realized as element wise using inner product, can be recognized as column by column using matrix vector product, can be recognized as a sum of matrices using outer product matrix. So, you should be able to express C is equal to summation A star j B j star j is equal to 1 to n. So, this is the column, this is the row, outer product. I am picking all the rows, all the columns and all the rows. So, C is the sum of n outer product matrices. So, I am simultaneously introducing 3 methods for computing matrix product, element wise, column wise, and sum of outer product matrix wise. So, I could have used the matrix vector product method. Now, I am going to use the outer product method. So, let xj be a random variable which is the random matrix. So, we considered x as a scalar variable, x as a vector variable, now x is a matrix based variable. So, a random variable is x that takes a value xj, which is the outer product of the jth column and the jth column of A and jth row of B. So, this is the matrix. That matrix is scaled by the factor Pj. Pj is the sampling probability, sum of Pj is 1. So, this is the sampling now. So, what is Pj? Pj is the probability with which I pick the jth column of A and the jth row of B. So, I am going to combine the selection to get the outer product. So, E of x, the expected value of the random variable, xj times Pj. Xj, the denominator is Pj, Pj will get cancelled. So, simply summation A star j Bj star, that is AB, and that is exactly the expression I gave you. So, this is the exact product. Random variable is obtained by this matrix. The sum of these matrices multiplied by the probability is equivalent to AB. That means the expected value of the random matrix is equal to the true value of AB. That means x as a variable can be an unbiased estimator for estimating the product. Is an unbiased estimator. Now, what is the probability Pj? Pj is going to be defined by, now look at that, the columns of A may not be same, the rows of B need not have the same energy. So, I am going to consider together the energy in the columns of A and the rows of B together. So, what is the numerator? The numerator is the product of the energy in the jth column times the product of energy in the jth row of B. The denominator is sum over this product over all n j running from 1 to n. So, this probability adds up to 1, is greater than 0. So, this is a well defined sampling probability. In the matrix vector case, this choice of Pj depends only on the column. Here, the distribution of the energy of B may be different from the distribution of energy in A. So, to take into account the variations in this distribution of energy in the columns and rows of B, I am going to take Pj as a function of the product of the energies in the row of B and the columns of A, and that is given by the equation 3. Now, I am going to define a random variable. Please understand, I now know the sampling distribution. I can sample from this distribution with replacement. If I get multiple copies and take the average, I get a better result because the variance gets divided by the number of samples by which I am going to estimate. So, y is equal to 1 over s times summation of x of t, 1 over s times this. We already know the expected value of the sum is the sum of the expected value. The expected value of the individual term is AB. So, the numerator will be s times AB divided by s with AB. So, y is a good unbiased estimate of the product. So, I am going to estimate the deterministic quantity by a random quantity, and the y is given by this. That is a random quantity. So, what am I going to do? I am going to first define the distribution, because A is known, B is known, distribution is known. From this distribution, I am going to pick the row of B and the columns, corresponding column of A, do an outer product, scale it, and repeat it s times. The average of these s outer product matrices is the estimate. That estimate is unbiased. The variance of the estimate by the virtue of the same relation, the exact value of the variance is given by this. Now Pj's are picked according to the distribution in equation 3. So if you substitute Pj from the equation 3, you readily get an inequality which is similar to that in the matrix vector product. Here the variance of y is less than the product of the Frobenius norms of A and B divided by S, which is the equation 6. Wow, we have made a lot of improvement today. We are coming to the guts of the randomized algorithm. We understand the guts of the randomized algorithm by solving simple problem. Problem 1, matrix vector product. Problem 2, matrix product. So what are the implementation details? Let K1, K2, Ks be the S set of integers chosen in S trials from the distribution Pj. Then compute the average, which is 1 over S times summation of xi, which is the values repeated k times S. Now I can bring S to the denominator and I can divide the whole thing, the rows, by this. So I'm going to scale the rows by S times pk1, pk2, pks. So these are the first, these are the, no, I shouldn't say first, these are the S columns. These are the S column, column k1, column k2, column ks, S columns of the matrix A. These are the corresponding rows of B. So my matrix product is approximated by these two matrices. A is as is, B is scaled. I could have considered scaling of A instead of B. So I am going to call this matrix as C, I am going to call this matrix as P tilde. These are the chosen columns of A, these are the chosen rows of B scaled by SPK. Therefore, I am going to approximate A, B, m by n, n by p, by C is equal to m by s and s by p. The error bound in this estimate, so 7 provides the approximation. This approximation is an error. The error in the approximation is through the variance. The variance is given by the bound 6. Variance is given by the bound 6. So that should give you a very good idea of the matrix vector product. I will do one special case. If B is equal to A transpose, we can approximate the Gramian AA transpose. And if we can approximate the Gramian is a low rank approximation. I should be able to compute the eigenvalues and eigenvectors of a low rank approximation faster than the full rank approximation. There are several methods for computing first k largest eigenvalues. Special algorithms are available. So by invoking those algorithms, I can compute the eigenvalues of the Gramian, which are singular values of the matrix A. So when B is equal to A transpose, we start with variance of y. I simply need to be able to change B by A transpose. Therefore, the variance bound essentially becomes by changing the Frobenius norm of A by Frobenius norm of A transpose. But you need to understand the Frobenius norm and the Frobenius norm of transpose are same. Frobenius norm of A is the same as Frobenius norm of A transpose. Why? It is simply the sum of the squares of the elements of A. Even though as matrices A and A transpose are different, when it comes to sum of the squares of the matrices in A is the same as the sum of the squares of matrices in A transpose. So these two quantities in the numerator are essentially the same. So it becomes 4th power of the Frobenius norm of A divided by Pj minus this. This is a constant quantity that does not depend on P. I want to be able to minimize this with respect to Pj. Now, you can think of the numerators as A1, A2, An be positive real numbers. So, I am going to define a random variable which is Aj by Aj by Xj. Xj's are the probabilities. So, instead of calling Pj, I am calling Xj. Xj summation is 1. So, this one looks like this quantity. The denominator Xj's are playing the role of probability. We can see by extension of the simple example n is equal to 2, the general case, you can see this quantity becomes minimum only when Xj is equal to square root of Aj divided by sum of the square root of Aj, which is a quantity which is equal to Pj, and that is the exercise for you. This exercise play along the same way as the special case n is equal to 2. You can solve this by a Lagrangian multiplier. We talked about, so in summarizing today's talk, we saw the need for randomization algorithm to solve large scale problems. The need arises because I want to reduce the time. I want to be able to get good approximations. We talked about two-step prototype. The first step is the randomization procedure. Second type is the classical method applied from linear algebra, which I do not have to cover, but there are plenty of them. The more you know, the better it is. So, I am going to concentrate only on the part A, the randomization. We talked about 3 methods. One is getting random samples W and mapping to Yi. Another one is sampling the columns of A. Another one is random projection. Random projection based ideas, we have already seen the basic methods of calculation as in Johnson-Lindersdorf's lemma. We will come back to that later. So, we talked about the importance sampling, uniform sampling versus importance sampling. We talked about how to compute the importance sampling probabilities, general methods. We illustrated the general method by solving simple problems, matrix vector product, matrix matrix product.